Hello student, welcome to lesson number 5. In this lesson, we continue with capacitors and capacitance, but in here, we are going to discuss the capacitor networks. So we start with capacitors in series. Consider this arrangement. As you have seen here, we have capacitor C1, capacitor C2, and capacitor C3. Now in this case, we have that Q is equals to Q here is equals to Q here. In other words, we are saying that the charges across each, or the charges in each capacitor, or the charges stored in each capacitor is the same when the capacitors are in series. But when you look at the voltage, you have V1, V2, and V3. So the voltage changes, and it is different from C where we have V1, and it is different for V2, it's different for V3. So it implies that the charge on C1 is equals to the charge on C2 is equals to the charge on C3, which is equals to Q. But now, why is this the case? We have that this is so because once the battery draws an electron from one plate of the capacitor C1, if now the battery removes an electron from one plate, we have that the negative charge on a plate of C1 will induce a positive charge on one of the other plate of C2. And again, the negative plate of C2 will also induce a positive charge on another plate on C3. So the process is repeated until all the capacitors appear with the same amount of charge. But we know that our V total is equals to V1 plus V2 plus V3. Therefore, the potential difference between each, or the potential across each of the capacitor, V1 will be given by the charge divided by the capacitance. So it will be Q over C1, then V2 will be Q over C2, and V3 will be Q over C3. So it implies that if now we come back to this equation, we want to get the total voltage, which is our V. We can now replace V1 with these values, V2 with this one, and V3 with this one. So by replacing, we have V is equals to Q over C1 plus Q over C2 plus Q over C3. But now our Q is common. So we can factor out Q, so that now we have 1 over C1 plus 1 over C2 plus 1 over C3. And by so doing, you will get that if you divide through by Q, this will be V over Q is equals to 1 over C1 plus 1 over C2 plus 1 over C3. But when you look at V over Q, it is the reciprocal of the capacitors. Therefore, it is 1 over C total, or the effective capacitance. Therefore, CT is the combined capacitance. So this is the formula that we are going to get the effective capacitance. And for us now to get CT, after adding all this, you're supposed now finally to get the reciprocal. But if you have only two capacitors, C1 and C2, which are in series, then we shall have 1 over C total is equals to 1 over C1 plus 1 over C2. And because they are two, we can be able to get the LCM, and the LCM will be C1, C2. So by dividing this, you get C1 plus C2 over C1, C2. But now you need to get the reciprocal to get the C total. So our C total now will be the reciprocal of this, which is C1, C2 plus, or divided by C1 plus C2. So this is now the special formula when you have, or when you are dealing with only two capacitors. Then from there, we have the capacitors in parallel. We are going to consider the arrangement of this one. We have C1, C2, and C3. They are all in parallel, but you know that the devices that are in parallel, the voltage across them is the same as the voltage of the external, or the external voltage. So the PD across each of the capacitor is the same as the PD across the source, since they are connected in parallel. So the total charge will be given by Q1 plus Q2 plus Q3. But we have seen that Q1 is C1V because the voltage is the same. Q2 is equals to C2V and Q3 is equals to C3V. Therefore, when now we get the sum, it will be C1V plus C2V plus C3V. But you can see that V is common, so we can factor it out. And by factoring it out, into bracket we are left with C1 plus C2 plus C3. So by dividing through by voltage, you find that Q over V is equals to C1 plus C2 plus C3. But now this term, Q over V, is our capacitance. Therefore, C, which is now the total capacitance, is equals to C1 plus C2 plus C3, where now C is our combined capacitance. So in case you have N capacitors, right, N, and they have equal capacitance C1, then the combined will be just N multiplied by the capacitance C1. So that way you are able to get the combined capacitance. We can look at several examples. We start with the first one. 3 capacitors of capacitance, 3 microfarads, 4 microfarads, and 6 microfarads are connected to a potential difference of 24 volts as shown in the following diagram. We have 3 microfarads, 4 microfarads, and 6 microfarads. One, we are supposed to get the combined capacitance. They are in series. Therefore, we use this formula. 1 over CT is equals to 1 over C1 plus 1 over C2 plus 1 over C3. So this will be 1 over 3 plus 1 over 4 plus 1 over 6. Getting the LCM, it is 12. You get the value as 0.75. But this one is 1 over CT. So to get CT, you get the reciprocal. And this term will be equal to 1.33 microfarads. Remember, all these terms were in microfarads. Then number 2, you're supposed to get the total charge. We know that Q is equals to CV. So we just substitute the values. 1.33 microfarads times 24, you get that the amount of charge is 32 microcoulombs. Then we're supposed to get the charge on each capacitor. Now, the capacitors are in series. And in series, we've seen that the charge on each is the same and is equal to the total amount of charge. So the total amount of charge we've calculated as that 2 microcoulombs. Therefore, the charge in each of them is equivalent to 32 microcoulombs. Then after that, we're supposed to get the voltage across the 4 microfarad capacitors. We just need to get this formula. V is equals to Q over C, but our Q is what? Our Q is 32 microcoulombs. Our C is 4, so you just divide, you get that the voltage across this one is 8 volts. From there, we have another example. The figure below shows 2 capacitors arranged in parallel. Work out their effective capacitance. We have it this way. 3 microfarads plus 4 microfarads. They are in parallel. So the total capacitance will be C1 plus C2, which is 4 microfarads plus 3 microfarads. You get that it is 7 microfarads. Then number 3, work out the effective capacitance for the circuit below. We have it this way. The 2 are in parallel and then they are connected in series with this one. So when you have this combined network, you first of all deal with this one, and then after getting the effective here, that effective will be in series with this one. So we proceed as follows. For the 2 parallel capacitors, we have that CT is equals to C1 plus C2. Therefore, it will be 1 microfarads plus 2 microfarads. You get 3 microfarads. Now, this 3 microfarads capacitor is in series with 6 microfarads. So again now, to get the effective for the 2 now, it will be 3 times 6 over 3 plus 6. And when you do that, you get that this one will become, if you multiply 3 times 6 is 18, 3 plus 6 is 9. So 18 divided by 9, you get 2 microfarads. So this now is the effective for this combined network. From there, we have another example. The figure below shows a capacitor network. Calculate the charge through 1.5 microfarad capacitor. We have it here. As you can see, we have 2 microfarads, we have 3 microfarads, we have 1.5, and we have 20 volts. So for us now to get, we first of all deal with this one that is in parallel. And for us now to get, you just get the sum. That is the effective capacitance for the parallel capacitor. You have 2 microfarads plus 3 microfarads, you get 5 microfarads. Now this 5 microfarads is in series with 1.5. So the effective capacitance will be 5 times 1.5 divided by 1.5 plus 5. And when you do that, you get that the effective will be 1.1538 microfarads. But we know that Q is equals to CV. So you just need to multiply the total capacitance with the voltage to get the total charge, which is 2.3077 times 10 to the power 5 coulombs. But now if you look at 1.5 microfarads, it is in series. It is in series with other capacitors. So it implies that the charge stored is the same as the charge stored in the circuit. And the charge from the circuit is this one, 2.3065 times 10 to the power negative 5 coulombs. Therefore, the charge stored in 1.5 microfarads is equals to this value, which is 2.3068 times 10 to the power negative 5 coulombs. From there, we have the assignment. Again, the assignment is testing what you have just covered. So make sure that you practice a lot and discuss with your peers. So thank you, and let us meet in our next lesson.